Quantum physics is a weird, wonderful world that governs the behavior of the universe's tiniest building blocks. It's like a secret code that unlocks the mysteries of atoms, photons, and all things subatomic. Buckle up as we embark on a mind-bending journey into the quantum realm, where the impossible becomes possible. Imagine a world where objects can be in multiple places at once. Picture particles that talk to each other faster than the speed of light. This is the reality described by quantum physics, a realm that defies our everyday intuition and challenges the very fabric of our understanding. In this strange realm, we encounter particles that behave like waves and waves that act like particles, a concept known as wave-particle duality. Uncertainty reigns supreme as we discover that we can never truly know both the position and momentum of a particle with perfect accuracy. The laws of classical physics, the physics of our everyday world, crumble in the face of these quantum oddities. Join us as we delve into the heart of quantum physics, exploring its most mind-blowing concepts and their profound implications for our understanding of the universe. One of the most mind-boggling aspects of quantum physics is the idea of wave-particle duality. In the macroscopic world, we are used to things being either waves or particles. Waves, like those on the surface of water, spread out and interfere with each other. Particles, like tiny marbles, are localized and distinct. However, in the quantum realm, things get fuzzy. Particles like electrons, photons, and even atoms can exhibit both wave-like and particle-like behavior. Sometimes they act like tiny localized points, while at other times they spread out like ripples on a pond. Think of light. We often describe light as a wave, and this explains phenomena like diffraction and interference. But light also comes in discrete packets of energy called photons, which act more like particles. This dual nature of light, being both wave and particle, is a fundamental concept in quantum physics. Imagine a coin spinning in the air, not yet landed. It's neither heads nor tails, but a blurry combination of both. That's superposition in action. In the quantum world, particles can exist in multiple states at once until measured. Think of an electron's spin. Instead of spinning in a fixed direction like a top, it can be in a superposition of both spin-up and spin-down states simultaneously. Only when we measure its spin does it collapse into one definite state. This concept of superposition is crucial to understanding quantum computers, which exploit this ability of quantum bits, qubits, to be in multiple states at once to perform calculations at speeds unimaginable for classical computers. Entanglement is arguably the most bizarre and counterintuitive phenomenon in quantum physics. It describes a special connection between two or more particles, where they become linked, no matter how far apart they are. Imagine two coins flipped simultaneously, landing on opposite sides. You wouldn't be surprised. However, imagine two entangled particles, miles apart. Measure one particle's spin as up, and instantly, you know the other particle's spin is down, even without measuring it. Einstein famously called this spooky action at a distance. Information seems to travel instantly between entangled particles, violating the speed of light limit. This strange connection has profound implications for quantum communication and teleportation technologies. Section 5. The double-slit experiment, a quantum puzzle. The double-slit experiment is a classic demonstration of the wave-particle duality of matter. Imagine shining a beam of light at a screen with two narrow slits. You'd expect to see two bright bands on a background screen where the light passes through the slits. However, something remarkable happens. Instead of two bands, we observe an interference pattern, a series of light and dark fringes, as if the light waves passing through each slit interfere with each other. This proves light's wave-like nature. Now, shoot individual photons, one at a time, towards the slits. You might expect each photon to go through one slit or the other, creating two bands. Instead, over time, the same interference pattern emerges, as if each photon interferes with itself. Even more bizarre, if we try to observe which slit each photon goes through, the interference pattern disappears. This experiment showcases the baffling reality of quantum superposition and the observer effect. Section 6. Quantum tunneling through walls of impossibility. Imagine throwing a ball at a wall. It bounces back, right? In the quantum world, there's a chance the ball could pass right through. This is quantum tunneling, where particles can pass through energy barriers that classical physics deems impenetrable. Think of a particle as a wave. Even though its highest probability is to be reflected by the barrier, its wave function extends beyond the wall, meaning there's a non-zero probability of finding it on the other side. The thinner the barrier, the higher the chance of tunneling. Quantum tunneling is essential for many phenomena, including nuclear fusion in stars and the operation of transistors in our electronic devices. It's a testament to the probabilistic nature of the quantum world. Section 7. Quantum versus classical, a different set of rules. Quantum physics and classical physics offer vastly different explanations for how the universe works. Classical physics, governing the macroscopic world, relies on determinism. Knowing the initial conditions of a system, like the position and velocity of a ball, allows us to predict its future with certainty. Quantum physics, on the other hand, introduces uncertainty and probability. We can only predict the likelihood of a quantum particle being in a particular state, not its definite future. This inherent randomness arises from the wave-like nature of matter and the act of measurement influencing the system. Furthermore, while classical physics treats energy as continuous, quantum physics reveals that energy comes in discrete packets called quanta. This quantization of energy has profound implications for understanding atomic structure and the interaction of light and matter. Section 8. Quantum applications. From lasers to computers. Quantum physics is not just a theoretical curiosity. Its principles underpin many technologies we rely on today. Lasers, for example, exploit the quantization of energy levels in atoms to produce highly focused beams of light, used in telecommunications, medicine, and countless other applications. Medical imaging techniques like MRI or magnetic resonance imaging rely on the quantum properties of atomic nuclei to produce detailed images of our bodies. Modern electronics, including smartphones and computers, depend on transistors, which function thanks to the quantum phenomenon of electron tunneling. Looking ahead, quantum computing holds immense promise. By harnessing superposition and entanglement, quantum computers could solve problems that are intractable for even the most powerful classical computers, revolutionizing fields like medicine, materials science, and artificial intelligence. Section 9. The Quantum Future. A world of possibilities. Quantum physics is a rapidly evolving field with the potential to revolutionize our understanding of the universe and drive technological advancements for decades to come. As we delve deeper into the quantum realm, we can expect even more mind-boggling discoveries that challenge our intuitions and expand the boundaries of what's possible. Quantum communication networks promise ultra-secure communication channels, unbreakable by any known means. Quantum sensors offer unprecedented sensitivity for applications ranging from medical diagnostics to earthquake detection. Quantum materials, with their exotic properties, could lead to the development of superconductors that operate at room temperature, revolutionizing energy transmission and storage. The future of quantum physics is bright, filled with exciting possibilities for scientific breakthroughs and technological leaps. As we continue to unravel the mysteries of the quantum world, we open doors to a future limited only by our imagination.